Good day. Let's get started again. So last time we left off at the powers, exponents, and we're going to keep doing exponents probably for a little while. So if we keep going with it, now let me. We talked about how negative powers went with reciprocals, like the negative. For example, if we had like 5 cubed equals 125, then if I cut right to the chase, last video we did this. 5 to the negative 3 equals 1 over what we got earlier, 125. It's the reciprocal of 5 cubed. So keeping that in mind. Now, let me introduce a new rule that it's going to come in handy. Let me go to Insert, Equation, and let's do this. Let's do x to the power of m as in Michigan plus n as in Nebraska equals down here. X to the power of m as in Michigan times, let me do times sign, x to the power of n as in Nebraska. So, like that. And let me also do, sort of the analogous rule. If you minus and subtract, now m and n can, if you subtract, you get that. Okay. Now, I technically would have to put restraints on this, but this is true. It's certainly true for all positive x. If we assume if x is positive, then m and n can be any real number, right? M and n are in the real numbers, so m and n real. And the way we write that, if m and n are in the real numbers, I don't want to get theoretical, okay? But we write a little funny symbol. That means m, n are in elements of the real numbers. They're either a rational or an irrational number, m and n. X, there are situations where x can be negative. I'll relax that in a minute. But if x is negative, m and n can be integers. So I don't want to get too theoretical. But the whole point of the matter is x to the power of the sum of m and n is the product of x to the m, as in Michigan, times x to the n, as in Nebraska. That's what I'm really wanting to bring on home. And likewise, x to the power of m as in Michigan minus n as in Nebraska is x to the m divided by x to the n. And if you want to write that in fraction mode, x to the n as in Nebraska would go down here, and x to the m as in Michigan would go up here, like that. And again, now, I don't want to get too deep into restraints, things we'd have to, conditions. It's the same condition we had up here for now. But x can be negative sometimes too. Of course, we have to be more careful about who m and n are if x is negative. But if x is positive, here I have to actually better insist x be strictly positive. Here, x could be, I better not let x be 0. If x is positive, we're good to go. If x is positive, we're good to go. We can use any real number, m and n, okay? And I want x to be positive so I can fly free and do my thing. But m and n could be they could be negative, they could be like a negative irrational, they could be, m could actually be like negative 15 and n could be positive pi. We could have all sorts of things, and this rule would still be good as long as x is positive. But let's look at some examples. But we usually keep x's as just in variable format. Now, for well, let's apply the rule. And I'm 5 minutes in. So if I apply this top rule up here, how about I call this rule 1? So if I call this rule 1, and I'll call this second one rule 2. So with rule 1, let me give you an application of rule 1. How about I put it underneath rule 1 so we can see? We'll get to rule 2 in a minute. Insert equation. So if you can go either way with it. So if I have x to the power of 5 times x to the power of, let's say, 6, that would be x to the power of 11 by the rule. So if m is 5, m is in Michigan is 5, n is in Nebraska is 6. Well, I started actually over here. If m is 5 here, Michigan is 5, n is in Nebraska is 6 here, we actually jump over here and get 5 plus 6. So let me create the intermediate step. So I'm correct, but let me put all my steps in. So we got 5 plus 6 here, by the rule up here. And we know 5 plus 6 is 11, is indeed 11. So we have 11. So by the Michigan plus Nebraska rule, or by the product of this is the product of exponents rule given the same base. We add we bring them together and add them, like we bring the 5 and 6 together additively, and we get the 11. We bring Michigan and Nebraska additively together. Now, on the other hand, we could do other things. Let me stay with rule 1. Now, 5 and 6 were real pretty, but we don't have to keep it. They can be quite disagreeable. I could have x to the power of negative 14. Well, that's not disagreeable. They could just be different. Times x to the power of 55. Now, that's x to the power of negative 14 plus 55. So that's x to the power of, well, by arithmetic, that's 55 minus 14, right? And that's going to be what? 41, I think. Yeah, 41 by arithmetic of negative numbers. This can go all sorts of different ways using rule 1 here. Now, you would think this would get boring, but now you can spice it up a little bit. Like you can have something convoluted. We're just using x. You could use p and q, but that's not all that exciting. Notice that if you have like p, or how about let's do j times j, that's understood to be j to the 1 times j to the 1, right? So that's j to the power of 1 plus 1. Of course, this is boring, right? And that's equal to j to the 2, j squared. Of course, j times j is j squared, right? That's not very entertaining, right? J to the 1 times j to the 1 is j to the 1 plus 1, which is j squared. This definition is consistent. But let me show y'all something. You remember how we defined j to the neg 1 to be the reciprocal? It's going to make sense why we defined it that way if I show you this. J to the neg 1 times j to the pos 1. Well, that is by the rule. If we use the rule, we get neg 1 plus 1. Well, we get j to the 0 is what we get, and we define that to be 1. All these rules had better sort of jive and be sort of self-consistent, or we're in some trouble. But they're going to be fine because, well, I got 1. But remember, we've also defined things this way. J to the neg 1 times j to the 1. Well, we've defined j to the neg 1 to be 1 over j. And we've defined j to the pos 1 right here to be j, right? But 1 over j times j is 1. Hey, because by reciprocal arithmetic, right? You remember by arithmetic, j is j over 1, and these right here, and then afterwards, across this diagonal right here, they cross cancel. We get 1. Yeah, you know, we're in agreement, doing it the rule 1 way or doing it the classic way. So yeah, you know, we have agreement. You know, if you do it, you can do it the rule 1 0 power way. You know, so it's pretty cool. You know, we have agreement with, you know, rule 1 calls this good agreement. And indeed, you know, negative 1 plus 1, you could look at that as 1 minus 1 if you wanted to. Either way you want to look at it. I just did negative 1 plus 1 is 0 because I knew that it was. Now, if I go down to rule 2, which I've almost scooted too far down the page here, rule 2 is just pretty much the brother of rule 1. We're just letting, you know, we're just adding negative in is what we're doing. But you could look at this as x to the m times 1 over x to the n, but let's not get too theoretical. Now, if I do, let me just use an example. If I have x to the power of 11 times x to the power of, well, no, let me do divide. I'm doing this rule now. So divided by x to the power of 8. Well, you know, we know from really algebra 1 and 2 that this is x cubed, canceling 8 of the 11 x's, but let's see that the rule is consistent. You know, by the rule 2, you know, that's m minus n. Michigan is 11, in this case, minus Nebraska 8. And yeah, that's x to the power of the 3, x cubed, right? So we get, you know, it's consistent with algebra. You know. So yeah, that, you know, we get consistency. Now, I tell you what where rule 2 can get a little strange, and it just trips students up who are uncomfortable with negative numbers. Let's say we get x to the power of 10 times x to the power of, well, what if I did negative 6? But not times, excuse me, divide. What if I divide by x to the power of negative 6? Now, you can't just subtract. We're not timesing, right? You would do 10 minus 6 if we were timesing. We're dividing, and the rule is Michigan minus Nebraska. So we're going to do 10 minus negative 6. But be careful, you know, that's 10 plus 6, right? That's 16. You know, by the rules of PEMDAS and arithmetic and all that, that's x to the 16 power. You got to watch out, right? Some of those things can get you. You know, this was straightforward. This wasn't. And now let me do one that's straightforward. I've got a minute to play with and a half. So equation. Now what if I have x squared divided by x to the 9th or something? Well, that's going to equal x to the power of 2 minus 9 regular. That's x to the power of negative 7. But remember how we define that? That's 1 over x to the 7th. And notice that's consistent with algebra 2, because in algebra 2, you know, if we wrote this in fraction mode, I'm about to run out of time. We'd get x to the 9 down here. We'd get x squared up here. And we would expect 2 of these x's to kill 2 out of 9 of these x's down here, and to get just a understood 1 left over up here, and to get the remaining 7 x's that didn't get chopped off down here. We cancel 2 x's up here, and 2 down here. You know, we have x times x up here, and we have x times x times x times x 9 times down here. But 2 of these x's, we cancel 2 x's up here and 2 x's down here, leaving 7 down here, and no x's at all up here, but that leaves a default multiplicative identity of 1. Remember, 1's the multiplicative identity, so you have to have it up here. I'm out of time. See you next video.